Good morning. Hi, everybody. Great to see such a large crowd. My name is Prorok. I'm a faculty member in the Department of Computer Science and Technology. My area of research is multi-robot and multi-agent systems. We're interested in developing algorithms and also system design, actually, for systems of, oops, I can actually hear myself here. Can I turn this off? Is there a way of turning this off? I hear playback. Oh, actually,
Maybe you need to move.
yeah. Okay.
You have to actually no, but
There.
it's just
It's all good. It's good. It's good. Thanks. Okay, so we develop solutions to get groups of intelligent agents to work together to solve higher order problems. And today's tutorial is really going to be about teaching a couple of the methods we've been developing in the realm of machine learning to solve a couple of these problems. So just to kind of give you a bit of an idea from the outset, this is actually really, really new stuff. So although the field of multi-agent systems and machine learning in the field of multi-agent systems has been around for quite a while, it's only been applied to the field of multi-robot systems in the last 5 or 6 years. So it's pretty new stuff. And hence, a lot of the things I'm going to be showing you are solutions we've developed that have been shown to work quite well. But I'm also going to spend quite a bit of time talking a little bit about the frontiers of research and problems I think are interesting to tackle. All right. So what actually motivates the research that we do in my lab? So one of the things that we're really excited about is this prediction that by 2035, there'll be over 1 trillion devices that are going to be connected, right? So this is not only robots and your autonomous vehicles and stuff, but also just generally cyber physical systems. So embodied intelligent agents. And what we do is we develop the algorithms that allow these intelligent agents to exploit these interaction channels. So usually it's some form of narrowband communication channels to get in touch with each other, coordinate, share information, and solve bigger problems than they could solve just by working on their own. So that's really the mission of the things that we do in my lab. So today's tutorial is going to be split up in 3 general parts. First, I'm going to say a little bit about why I'm so excited about collective intelligence. In part 1, I'm then going to talk about why multi-robot and multi-agent problems are hard and why we're actually interested in looking towards new upcoming methods to solve these kinds of problems. So beyond first principles, beyond exact solvers, beyond approximate solvers, looking more to data-driven methods. And to try to answer, convince you of the question why machine learning is an interesting way to go about this. In part 2, I'm going to be talking a little bit about a couple of paradigms we've started working on and developing towards solving these kinds of problems. I'm going to give you examples and references. More than half of these examples will be coming from my lab because these are, because there is not that much out there beyond that, and also because I'm very familiar with these works and hopefully can talk to them in more detail. And at the end, I'll be talking about the frontier of machine learning in this domain and the tools that we are using or that I think are useful to using towards solving these problems. So I'll make breaks throughout the talks. I'll also be happy to take questions throughout the talks. So feel free to raise your hand and interrupt me. So I really like starting out my talks with this little movie here of starlings. This is an example of collective intelligence. And what's really phenomenal about this, beyond it being really elegant and beautiful, is that in the real world, human systems, so human designed, engineered systems, have not been able to reproduce this kind of behavior yet. And I found this really, really mind-boggling. So we don't yet have systems of drones or autonomous robots moving in 3-dimensional space that can reproduce this kind of flocking, cohesion, herding behavior. So this really, shows us what is going on under the hood here is actually extremely complicated and complex, and yet probably very simple, but we don't really know. There are many, many approaches that have been designed. So some of you might know of Boyd's Reynolds algorithms, Reynolds flocking rules, etc. So there have been a lot of approaches towards flocking, but they only ever really solve a part of the problem. And why this is so interesting is because it's robust. So you can add a starling or remove a starling and nothing happens. It's anonymous, so they don't know who they are. The communication here is very low fidelity, so it's vision-based. There's no explicit communication channels. They react extremely elegantly to external disruptions, wind, obstacles, other environmental factors, and it just works. And we are really, really far away from being able to reproduce these kind of behaviors with engineered systems. So collective intelligence is really beautiful, and it's beautiful for all of these reasons. But what I also want to make clear is the algorithms and the ideas that go into collective intelligence are also practical. So by studying these kinds of underlying systems and natural collectives, we can actually learn something that is useful to us, especially now that we've been densifying in urban environments. We've been putting a lot of pressure on engineered systems, logistics systems, supply chains, and we need to look farther to see how we can solve these problems with creative solutions. So as soon as you embody multi-agent systems, I like to call them multi-robot systems. So we're talking about systems of, say, ground robots or aerial robots. And these are a couple of the applications you probably all are already quite familiar with. So Amazon. Around 2000, Amazon bought Kiva Systems, formerly a startup, which designed those orange-looking ground robots for a couple million, actually. Pretty much of a bargain if you think about what they've done with the Kiva system robots since then. They just a few weeks ago released a new robot that has additional autonomous capabilities. And what Amazon uses these robots for is to do everything that is within the perimeter, right? So you have your associates around the perimeter of the warehouse systems that retrieve items from the stacks and actually do the packing into the boxes. But all the pick and place of produce is done by these autonomous robots in these modular warehouses. Ocado has a somewhat similar system, although the autonomy of the robots is different. The robots actually move on grids, and they pick and place from above into kind of hanging systems where they select the produce they've been told to fetch. So slightly simplified in terms of the mobility, and it's the deconfliction is easier because it's exact, it's on the grids, but more complicated in terms of the distribution of the produce into these bin type containers. So they offset the challenge to a different domain or a different aspect of the problem. Transport, so driving in fleets, driving in platoons saves energy. It's also helpful for lorry drivers who do incredibly long shifts and benefit enormously from assisted driving systems. Agriculture has seen autonomy come up as well for precision agriculture, for closed loop control of where robots have to go, say, sense the soil or plant seeds. And they work together in terms of where they have to go. This is a spatial problem, right? And spatial benefit of systems, less low-hanging functions, so environmental monitoring, where you're sending out drones or ground robots, data. That system within which to place the algorithms and the solutions that I'll be talking about later. Centralization versus decentralization is a big topic in multi-robot systems. And if any of you are not familiar with these concepts, just let me know and I'll do a little detour and explain a little bit what this deals with. And of course, dealing with failures is something that we care a lot about, especially as we deploy systems into the real world. So this movie here, I'm just going to play it out. I want you to kind of pay attention to what's happening here. So these robots are epochs. They're about this big. And they're solving a problem, a classical multi-agent problem here. And I'm just going to let you watch and see what happens. So this movie was filmed at EPFL. I was a PhD student there. I was part of this experiment. And what you're seeing here is an example of the multi-agent pathfinding problem. Okay, so this is an NP-hard problem if you solve it in the discrete domain. Here we're seeing an instance in the continuous domain. But what I want to ask you is, how is it possible that we solved this in 2014 when I was a PhD student, and we still don't really have exact solvers that can solve it at this scale, especially in real time? How did we do it? Anybody have an idea? A little bit of brain jogging for 9:30. Heuristics, yeah, could work. Heuristics are hard to get to deploy with this level of perfection. So as you can see, it just kind of like falls into place, right? But yes, heuristics, a lot of people work with heuristics. Yeah. Excellent. Somebody's awake this morning. So I was one of the lucky PhD students who was deployed to go catch the robots when they dispersed after having been placed in their logo in the beginning. And so this is, yeah, being played backwards. So that's just an example of, we wanted to do this video, but that was the best solution we had at the time to solve this problem, right? Okay, so here are the 3 C's of collective systems. We have coordination, coordination, cooperation, and collaboration. I really care about this because the community usually uses just one of these 3 to mean everything, but there is a distinction. At least in our opinion, and we actually recently put forward a paper that tries to delineate the differences a little bit more precisely. So coordination is, for example, a problem like multi-agent pathfinding. So every robot has its own goal. There's not much benefit in working with the others beyond you're just solving a bigger problem, right? So if you think about, for example, cooperative coverage problems, that's a problem of coordination, because if you add another robot, you're gaining 1/n in terms of time. Okay, so the benefits you gain from deploying coordinated systems are at most linear. Okay, cooperation is actually very similar to coordination, where again the goals of the agents don't necessarily need to be aligned. But if they are, there's a benefit for the system as a whole, okay? So in coordination, agents are trying to get out of each other's way. They all have very individual, distinct goals, and it's usually a problem of spatial distribution. In cooperation, examples are, for example, coverage or search of an area to find a target, and you have to relay information about this target through multi-hop communication back to a base station, right? And what's interesting about cooperation is that you need these individual agents to all get together, and only once we actually have a connected graph, right? So connected basically means there's a path from the target to the base station, do we solve the task, right? So if we have a limited communication range and the robots don't distribute adequately, we won't actually have a communication channel from the robots that are seeing the target to the robots that are communicating with the base station. So until the robots figure out how to lay themselves out on the ground so that they have a connection, we haven't solved the problem. So there's, again, linear gains, but there's potentially a threshold at which we make the jump to achieve these linear gains. And collaboration is an example where we're really looking at complementary skills, okay? So the robots can be heterogeneous or they can be homogeneous, but they're complementing each other, right? So you can think of collaboration like in the human case where people work together and you work together on a paper because different people are bringing together different skills. And collaboration brings superlinear gains because if you don't get in these additional skills, you can't solve the problem at all. There's no way you're going to solve it. Okay, so those are the three different C's of collective systems. Okay, I'm going to start to jump into a very concrete problem, and I'll convince you that this problem is hard. So you already saw an instance of this problem in the continuous domain. I'm going to introduce it in the discrete domain because it's easier to discuss. So the problem we're talking about here is multi-agent pathfinding, which is a very classical problem in the domain of multi-robot systems because it's pervasive, right? So it's the warehouse problem, for example. What you want is you have agents that start off at given origin positions, and they're designated to reach their destination locations, hopefully as quickly as possible, okay? We usually measure the quickness or the performance of these systems through make span or flow time, right? Make span tells you how quick you were timed by the last robot to reach its goal, and flow time is simply the sum of all robot travel times. The goal is for these robots to do this on collision-free paths as quickly as possible without getting into deadlocks, without getting into live locks. And those two constraints are actually very hard to achieve in some cases, and I'm going to show you why. So here we're assuming we have a labeled problem, which is generally harder than an unlabeled problem. So unlabeled problems means we have positions we want to fill, but we don't really care about who goes where. And then labeled problems is it's a specific robot that has to go to a specific location. So that's common when you have, for example, payload that you have to deliver at a specific location. But the logo filling video is an unlabeled problem because you wanted to fill spots, but you didn't really care which robot went where. Okay. All right. So why is the problem hard? So if you could think about it, you're like, well, how can it be that this problem is so hard? It looks so simple. But here's an example of why you need to couple the systems and you need to compute solutions by taking into account centralized information of scenario. So here we have blue and green that want to reach their goals. And if we simply let the robots move, you know, you press play and the robots start going, green will move, it'll sit at its spot. And what is blue going to do? Blue is going to be stuck in a deadlock. Blue will never reach its goal if green and blue move at the same time and they're not coordinated, right? This is important. So I hope this makes 100% sense to everybody, okay? So if you couple the systems and they compute their solutions in a centralized way through a solver that knows how to compute solutions for this kind of problem, what will happen is blue will pass the entrance to green's, you know, way out of its little cave there, and then green will move into its goal and blue will have reached its goal in the meantime, right? So this is why we need to couple these problems so that we actually ensure we are achieving completeness. So completeness in computer science basically means we found a solution and the solution exists. The solution is designated by the fact that all robots have achieved their destination, right? If 9 out of 10 achieve their destination, completeness is not satisfied, right? So that doesn't count, that's a failure, right? So it's quite a difficult thing to achieve unless you have centralized solvers that can do this. Okay, moving on, why is this problem hard? So if you think about this in terms of complexity, so here we have 3 robots. They each have their configuration space. Each of these agents' configuration space has m states. And so if you're solving this with a coupled planner or a coupled solver, the solver has to compute through m to the power of n states, where n is the number of robots, right? Now, if you're using, for example, an algorithm such as A star, I presume some of you are familiar with A star. Yep, quite a couple. Then you'll know that the complexity of solving a problem with m to the power of n order of states is roughly in the order, or the worst case scenario, m to the power of n. So what this means for us is we don't scale in the number of robots, right? We have an exponential complexity in the number of robots. So you can solve this on a desktop for 10 agents, no problem. 20 agents, yeah, you're at about 5 minutes. 30 agents, you're already at 10, 20 minutes. And soon you're like, I can't use this for my warehouse, right? So this is why multi-agent pathfinding is a relevant problem to be studying, because Amazon, when it gets a new request in, we have to go get this item from there. They can't just stop their whole warehouse, wait for 10 minutes for the solution to compute, right? And you might be thinking, oh, but then we can do incremental solutions that can deal with dynamic constraints. Yes, algorithms exist for that, but they're difficult to design. And so this is why we have been interested in studying those kinds of problems. So this is just a couple of points here. So multi-agent pathfinding is provably NP hard to solve. I'm putting the reference here for those of you who are interested. What's also interesting is that the make span and flow time objectives are they're conflicting. So you're on a Pareto front. You can't optimally solve one and optimally solve the other one as well. So you have to decide what you care about. You either care about the slowest robot, or you care about the average travel speed of all of the robots in your system. And here are a couple of researchers who are very active in the domain of exact solvers, approximate solvers towards this problem. A little detour. So what I've been showing you thus far is assuming a centralized observation. So this is what a lot of you will be familiar with from a lot of the research you've been seeing in the field of reinforcement learning and games, because many researchers assume, oh, yep, we have a global observation of our space. We know the full, state of the game, we know the full state of the robot distribution, and hence I just have to give that to my solver. But actually, in many real systems, you don't have that information, especially if it's very dynamic, or you simply don't have a bird's eye view, or you're relying on local communication channels to pass on information. And so another field that actually tackles with the sequential decision-making problem is research in the field of MDP, so markov decision processes. And I believe many of you here will be familiar with them. So why MDPs are interesting to us is because the generalization of MDPs is partially observable MDPs, where we don't assume that we have global information of the state space. And an even larger generalization of POMDPs is decentralized MDPs, where we actually have multiple distributed agents that only act upon local observations and base their decisions based on those local observations, okay? And so here are a couple of complexity results, which the reference are there, and you can look at them if you're interested. But all of this is just to say that solving partially observable MDPs or decentralized POMDPs is a really hard problem again. Okay, so I'm soon wrapping up the first part, showing you a couple of different examples of why multi-agent problems are hard. This is a video that is an example of cooperation. So you remember that cooperation is an example of where individual agents have their own goals and they'll work together if they have to, but if they do, they will suddenly reach this threshold where the system really takes benefits from them working together really nicely. And the full video is on YouTube. I'm only going to be playing a part here for the sake of time. But what you see happening here is, so this is something we did in my lab a few years back, is we're artificially creating a bottleneck in this traffic scenario. And what you see happening is the agents that are in the inner lane, the agents that are in the outer lane are ever so subtly slowing down for the agents in the inner lane to pass by. I'm just going to play it again because you hardly see it happening. And it's really interesting if you actually juxtapose this with the non-cooperative scenario, because in the non-cooperative scenario, what happens is you have a bottleneck. Cars in the inner lane just start queuing up behind the stopped car and nothing is moving anymore. And here, what's interesting is that the change in behavior from the cars on the outer lane is imperceptible. So it's very subtle. So they're taking a minor hit to their local incentive, which is, I want to get home as quickly as possible. But the benefit to the system overall is we get over the more than 30% increase in throughput if we work together. And it's cooperative because if one car is doing this, or just two cars, you're not really gaining very much. But if 10 cars, or say all of the cars in the system are doing this, you actually really start gaining a benefit and seeing the advantage of doing cooperative driving. Okay, and this is the last example. So this is some work by Ralph D'Andrea at ETH Zurich, which, let me just play this through. Yeah, I'm going to play this through, and I'm not going to say much until the end, just so you can kind of try to guess what they're doing here. So this is a really nice example for two reasons. So it's an example of collaboration. The robots need each other to tie the knots to create the bridge, right? One robot by itself couldn't have done it. And it's really nice also because it has a lot of actually it has a real world purpose. There are a lot of places around the world where bridges are needed in a very urgent and impromptu manner, and they don't necessarily have the facilities or skills to build them. And that is one of the things you can do with very easily deployed autonomous systems. Okay, so I'm going to summarize now the reasons of why developing solutions for the 3 Cs is interesting and very relevant. So I've convinced you of the fact that coordinated decision making is a hard problem for various reasons, be it because you're tackling in the discrete domain or as well in the continuous domain. There are benefits from getting the robots to talk to each other. So you can really benefit from exploiting explicit communication channels. Right? You could technically say robots are just going to be basing their decisions on local observation fields, but if you exploit communication, you're going to have access to more information, so the unobservable latent variables. The question, however, remains how and what and to whom and when are robots going to communicate? And designing algorithms that account for that is, again, difficult, and multiple works have discussed that. And finally, even if we can solve the first 2 boxes, we're still facing the problem of robustness and resilience, because real-world systems are susceptible to noise. What happens if a robot fails? What happens if a robot actually becomes compromised? What happens if communication fails? We get delays. All these things happen. And many first principles algorithms do not deal with that so well. So yes, you can model noise distributions. Yes, you can model various things, but the assumptions are usually quite restrictive, and we need to think about these kind of problems much broader. We need to think about resilience beyond robustness. So clearly, we can go about this designing exact algorithms, first principle-based approaches. The last 2 decades worth of work really has gone into that a lot. And what's very, very recent in this domain is data-driven approaches, and that's what I'm going to be talking a little bit about next. Okay, so part 2. I'm going to introduce a couple of paradigms, and I'm also going to spend a little bit of time talking about learning communication, which is something that we care about in my lab, and hence we'll spend a little bit more time on that as well. This is going to be, by no means a very comprehensive overview of the field. So in the last, I'd say maybe 2 or 3 years, there's been quite a bit of movement in this area. But I hope that by talking about these 2 or these 3 concepts and ideas, you'll have an idea of the area and why it's interesting, and we'll let you explore the field more generally. So imitation learning, I'm probably repeating things that you already know, but it assumes that we have an expert algorithm that can solve the problem of interest, and we're going to be copying that expert algorithm to hopefully do better than that expert algorithm can do in certain other scenarios, right? We're hoping that somehow the solution will be able to generalize. So that's the hope we have from exploiting imitation learning solutions. Reinforcement learning is interesting because not only don't we need an expert even if we have one, but sometimes, and especially when we're looking at complex behaviors, we don't know what the optimization objective looks like, right? We don't have a solver for many difficult problems. And what reinforcement learning gives us instead is a way of designing this optimization objective in a slightly simplified way through the idea of reward shaping, right? This is good and as well bad, because the problem of reward shaping until this date is a little bit of an art. So reward shaping in some scenarios can be very simple and trivial, and it can be robust to different formats. But in many scenarios, your reward, if you design it correctly or incorrectly, will be the make or break of your task. And finally, I'm going to talk a little bit about specifics in the sense of what we care about. So we care about developing solutions that we can deploy to large-scale systems that function in real time as a function of quickly changing incoming information, and hopefully also in a decentralized manner. So we want to relax this assumption of, okay, each agent needs to have full information of the global state space. Okay? So we want solutions that can be either based only on local observations or that can function with local observations and also exploit learned inter-agent communication strategies. Okay. So this is a little bit of a tour of what we're going to be talking about. So the core question here is, now that we know that there are a lot of interesting problems that multi-agent systems can solve, can we actually teach them? Can we design learning systems that will allow them to learn how to interact? And beyond just simple interaction, can we actually teach them or design learning systems that allow them to learn explicit communication strategies, right? So really imagine that instead of robots sending each other interpretable messages that we have designed, right? These are the variables you're going to be packing into your messages. We're telling them, you decide what latents go into your package and you send that latent out, and I have no idea what's in that latent because it's a learned strategy, okay? So this is kind of the framework I want you to have in mind as I talk about these things. And as these systems, as our agents become equipped with these decision-making policies, they will learn how to aggregate and make decisions based on the messages they receive from their neighbors, as well as the local observations they make within their field of view. So imitation learning, what's the idea here in terms of multi-agent problems? So I hope that this kind of representation here in 2 dimensions helps you also categorize what we're trying to do here. And our idea is the following. So we have exact solvers that can solve small problems offline, assuming full information, right? That's an example of exact multi-agent pathfinding solutions, for example, right? So that's that first box on the upper right. So we have very good algorithms that can do that. As we go to very, very, very large systems, we need to, introduce heuristics. We need to introduce approximations, and we obviously there's a trade-off. We will lose precision, and that's okay. But we're certainly still operating in the realm of centralized and full observation state systems. Okay? Now, if we move down the axis to the bottom here. Okay, say we can still deal with small problems, but we really want the systems to work online and our robots are working with partial information. I have solutions for this for systems of say 3, 4, 5 robots. And most of the literature in the field of multi-robot systems deals with problems in this regime. So 4 or 5 robots, partial information, they're all functioning online. Many of you will probably have seen videos of 3, 4, 5 robots doing something. And yes, we have solvers for this. But what we really want to do, so our holy grail is this one there, right? We want really big systems of robots. We want them functioning with only local information. We want them running in real time, reacting to incoming information, and they're hopefully also decentralized. So they don't need to rely on centralized information. And so what we're going to do is we're going to leverage other solutions that we have. So these 3 boxes here are our experts. And we're going to try to find out how can we use these experts to bring together data that we can learn from in an imitation learning setting to generate solutions for this orange box, okay? So that is the idea we're exploiting in our work towards solving those kind of problems. Okay, one more thing before I go into one concrete example. So data science or data-driven approaches are successful when our inductive biases make sense. And the bias we're going to be using here for multi-robot systems is saying that agent-to-agent relationships can be represented as graphs. So the interactions that we're modeling here they essentially we have an analogy that is given to us through graph topologies, right? And yes, surely these graph topologies are dynamic in time. So as the robots move, as they're interacting with other robots across time, these graphs change their shape and form. But the graph analogy holds, and we're going to be using this, this idea in order to structure our data to learn from it in a more effective way. And so the workhorse for this kind of inductive bias is graph neural networks. And I know that there's another talk in the tutorial going to be focused explicitly on this, so I'm not going to delve too much into GNNs, but I just want to say a few things of why GNNs are so interesting for multi-robot systems. So yes, where they allow us to exploit the underlying graph structure of the data that we're going to be producing. And what's super interesting to us are their permutation, equivariance, and stability. So those are two theoretical properties that GNNs have that are crucial to making them work for multi-robot systems in an efficient way. So why is permutation and equivariance so interesting to us? Well, it's interesting because if I receive data from one person here and one person here, the order does not matter. And if I permute those two pieces of information in my graph, unless they're connected to some other local observation, the order or the relative observation that I have from these agents does not matter either. So we want this permutation equivariance to hold so that we can use the data efficiently as we aggregate messages from neighbors in our graphs. Stability basically means that if we have small perturbations in the structure of our graphs, the policies that we're learning through these GNNs will still perform similarly. Okay? And so permutation equivariance and stability have both, or stability in particular has been proven in this paper, but permutation equivariance has been discussed in many papers on GNNs. And I'm sure Petar will also speak about this, I think, on Thursday. And the final thing that is unique to us, so multi-robot scientists using GNNs, is they can intrinsically be distributed because of the mathematical models that we use in order to write them down. Okay. So the formulation of GNNs allows us to run decentralized policies. And I'll spend quite a bit of time talking a bit about that in the next few minutes. So the first case study that I'm going to talk about is a case study on multi-agent pathfinding. The question that we're going to be trying to answer here is, can we somehow automatically synthesize local communication and decision-making policies to solve hard coordination problems? Okay. So we're looking at the multi-agent pathfinding example. And we're going to say, okay, we're going to try to solve this problem, but we're going to try to solve it based only on local information, which is different from what centralized solvers do. And we're going to try to exploit communication channels in order to do this. Okay, so here's the problem setup. We have an agent, here agent number 4, that has a local field of view. And agent 4 has a designated destination, so a goal position. It does not have a reference frame, so it does not know where its position is, and it does not know where its goal position is, but what we are giving our agents is a direction to the goal. Okay, so this directionality is projected onto the perimeter of its local field of view. What the agent can also see is black boxes, so obstacles in its field of view, and it can also see any other agents that might be moving around within this local field of view. Okay, so what we're going to do with this is we're now going to try to derive a local policy based only on what it can see in this field of view, as well as incoming messages from neighboring robots that will hopefully allow the agent to not only solve the task, so we're looking for completeness here, but also reach performance comparable to centralized near-optimal solvers. So very ambitious, but we're going to try to do this, okay? And what's important is the yet scale more gracefully part, right? Because we know that these optimal centralized solvers do really well at the small n regime for n, where n is agents. But as we scale those systems, they start to stall, and that's where we want to do better. Okay, so this is how we set the system up. And this is not by all means an architecture that is the only way to go. It's an example, okay? And this is, it's an end-to-end learning way of viewing the problem, and it worked very well for us, and I think it's an interesting way of thinking about things. So we start by saying that we have a local observation, which is given by this matrix Z. We're going to input that local observation into a CNN, which will process this local observation and produce a value X. That value X will then be fed into our GNN, which will produce a value x prime. That value will then be fed into an MLP, multi-layer perceptron, and will then output our final action, which is in this particular case in the discrete domain, because we're modeling it as a multi-agent pathfinding problem, which means that the agent can either decide to stay still or move up, down, left, and right. Okay. So this is our pipeline. And as you can see here, we're going to be learning 3 sets of parameters. One, which is the set of parameters that tells us how we process our local fields, our local information. One set of parameters, that's theta 2, which tells us how we generate and interpret communications. And one set of parameters that tells us how are we deciding what to do, so our action policy. Okay, so this is how we set the system up, and I'm going to talk you through how the GNN actually comes into play here. And the reason I'm doing this is because I will hopefully convince you of 2 things. A, that we can train these things very efficiently in a centralized manner, and B, when we deploy them, so at runtime, they are intrinsically decentralizable. Okay. So what are you seeing in the first equation? So the first equation is basically just telling us how an agent I aggregates information from its neighborhood. Okay. So in a centralized world, S is an adjacency matrix, and X is a vector of information coming from agent J. Yes.
So once you define these neighbors, are they just the nearest neighbors in terms of without the field of view? So that, for example, I rank all the distances and then take the top n or something?
Yeah, great question. So S is an adjacency matrix that assumes that we've defined, for example, a communication range. So the size of S is defined by the number of agents, and where we put 0s and 1s is defined by our maximum communication range.
So you have a limit in terms of like how far
Yes.
do you communicate?
Yes, you can have a very small one, you can have a very big one. We actually have results on that. I'm not going to be showing them today, but we can talk a little bit more about what changing that variable does to the system. And it's counterintuitive, just to say that from the get-go. Okay, so S is our adjacency matrix. K are actually communication hops. So if you only have a one communication hop system, so I'm only talking to my neighbors and that's where my communication stops. K is 1, you don't need to necessarily model it, but in some systems we're actually interested in multi-hop communication. So I get, like, I can talk to maybe you and you can talk to somebody else, and then I get information from that guy as well. Okay, so that would be a 2-hop communication system. And so you can sum over your neighbors and you sum over your communication hops, and then you aggregate all that information, and Sx sub I is the information that an agent I has aggregated over this centralized way of formulating my communication system. Bearing in mind, S is actually time varying. Okay, so T here is not an index I'm showing because it shows up everywhere, so we're just removing it. Okay, and so the magic happens in the second equation where we multiply all of this by H, and H is my learnable parameter. So H is going to be telling me how am I going to be interpreting these incoming vectors X from my neighbors that are represented in S, right? So H is my learnable parameter, and I show that here through a bank of matrices that then compose theta 2. Obviously, if I just have one communication hop, I just have H, and theta 2 is equal to H, okay? So remember that I have this kind of end-to-end learning system where I'm learning not only the communication strategy, which is what I'm showing you here, but I'm also learning theta 1, which was my CNN, and theta 3, which was my MLP. And so I'm going to be learning all these 3 parameters, and my loss function here is actually cross entropy, because it's a discrete system. If you have a continuous system, you would use a continuous loss. So there's no, so you can generalize over that. And so once I have this set up, I'm actually ready to go, assuming that I know how I'm going to generate my data. And I'm going to say a little bit about that at the very end. First, though, I promised you that the reason I was showing you the math was because I wanted to convince you that training can be done in a centralized manner, yet execution is intrinsically decentralized without changing anything to our system. And this is how it works, okay? So very simple if you think about it, but I do want to just walk through the motions, okay? So let's assume that A is an ego agent here. Every agent makes a local observation. The local observations here are going to be X sub A, X sub B, X sub C. And A is going to be receiving these over an explicit communication channel from its neighboring agents, okay? So let's say X sub B here observed something in its local observation field. It fed that through its CNN, the parameters of which it is carrying locally. And the result of that pre-processing resulted in X sub B. And X sub B is what it then sends over this wireless channel to all robots that happen to be hearing what it can say, okay? So parameters are carried locally, agents aggregate messages, and then what do agents do when they receive the messages, okay? So now here from a viewpoint of agent A, we have at the 0th hop, we're just saying this is agent A's own message. So it processed its own local field of view. And now it's multiplying that with H sub 0, which is the 0th communication hop, resulting in a latent. And it's also receiving messages at the first communication hop from agents B and C, which through the GNN formalism are first being aggregated and then multiplied by H sub 1. And you can see how the aggregation is very important here because it maintains the invariance over the size of inputs, right? We always have this H sub B, or this, the vector that is being multiplied by our learned parameter H is always the same size due to the aggregation that happens a priori. Again, we aggregate after our hops, and then we pass it through a nonlinearity. This gives us X prime, and that is what we pass through our MLP, which then decides how the agents have to move. So the key here is it's decentralizable because the parameters of the communication strategy are carried locally, the parameters of the MLP and also the CNN are carried locally, even though they were trained in a centralized manner, right? So centralized training, decentralized execution. All right, so I just want to show you a movie that shows you that this really works. There are quantitative results in the paper. I don't want to delve into those details, so I'm going to skip over that today. But what I want to show you here is qualitatively, it works very well. So a lot is going on here, but what you can see happening is on the left-hand side, the expert solver, and on the right-hand side, our solution. What is important to remember here is that the expert solver has all the information a priori, and this is just a playback. So that's how expert solvers work. They compute everything based on starts and goals, and then it's just a playback of trajectories that are fully defined a priori. So there's no online computation here. Our solution, however, is a sequential decision-making solution, right? The agents are running policies, and these policies are reacting based on local observations and incoming information. So every agent here is carrying its little, neural model, aggregating information from its neighborhoods, processing its local field of view, and basing its decisions on that. And you can see how qualitatively both solutions terminate at roughly the same time, which is a good thing, meaning that our solutions are efficient. Our solution doesn't get stuck, which is also very crucial because it counts for the completeness. And what I'm not showing you here, but what we have in results is that this solution here, it times out at 10 minutes at 40 agents. This solution here doesn't time out at 40 agents because it's run locally. And so you can already see how we're approaching this kind of holy grail of, wow, we're solving NP hard problems in a decentralized manner and we don't have computation bottlenecks, okay? So this is not the full truth, and I invite you to read the papers for the full picture. The problem is generalization, okay? So we know that, I'll come to you in a second. We know that if we train our systems on systems of 10, 20 agents, there is a drop in performance as we then deploy on systems that are significantly different from what we saw at training time. So if we train on systems of 10, 20 agents, we're going to be performing extremely well on systems of 10, 20 agents. We'll have a slight reduction in performance of systems of 30 agents, a little bit more at 40 agents, and so on and so forth. But we're still solving it incredibly fast, right? So that's the trade-off. And we have a series of papers that actually discusses how you can get over the generalization challenge. And we've used things such as attention mechanism and so on and so forth. And we have actually been able to show that you can scale these systems to 100x in terms of size with respect to the training instances solved with a minimal loss in performance. This is not to say that we've solved the problem of, solving these kinds of NP-hard coordination problems, but we know that it's a promising approach, and we're continuing to push along that frontier. There was a question.
Yeah. So have you considered some swarm intelligence algorithms for the multi-agent pathfinding problems? I don't remember the specific one, right?
Yeah. So swarm intelligence is a very big field. It's kind of overlaps with general, this idea of collective intelligence. Most of the approaches developed within the community of, swarm intelligence scientists are based on heuristics, which is good, which I'm not saying this is much different, but they will have the same kinds of problems. So completeness guarantees, you don't have them. And so then the question is, how can you design solutions that are efficient, yet also have completeness guarantees? The problem that you have with a lot of the heuristic approaches is that, so this kind of thing is very difficult to design, because here, even if you have heuristics, if you're armed with heuristics, how are you going to use them to design communication strategies? You have, even if you're basing it on hand designed heuristics, you still have to hand design a communication strategy. And this is where a data-driven approach really helps us, because we don't have to hand design anything. We're really copying expert algorithms that show us how it has to be done. Okay, a couple of practicalities before I close. Yeah?
In the previous picture, can you please comment on what these lines indicate?
Yeah, sorry. I somehow assumed it was clear. So we're always, when I play this movie, we're focusing on one agent. So here we're focusing on agent 20. The red lines are the one communication hop, and the dashed lines are the two communication hop. And then this particular scenario, we're just using two hop communication. So agent 20 is basing its decision on what itself can see and anything that it can receive from its two hop communication neighborhood. And actually the length of the lines here answers your other question, which was how big are the communication ranges? So that's what it is. Yeah. And so the counterintuitive thing here is you could argue, oh, well, if I just increase my communication radius to infinity and they can all talk to each other, it's equivalent to a centralized system. Actually, it turns out by using the framework as is in this particular in this framework, as I've shown you today, it deteriorates performance because you're getting so much information that you're not dealing with it very well anymore. And that's when you have to think about things like tension, other mechanisms to circumvent that.
So maybe the aggregation operator might have to change if
yeah,
like a lot of
that's what attention essentially does. Yeah. Yes. Yeah, you should come talk to my PhD student who's working on exactly that problem. Can introduce you later. Awesome. Yes.
The way it's solving the problem for me, and then it's really good. It's sort of you decompose the problem to solve a local problem with the graph that you use within this neighborhood. And then you also have the communication element. And I was just wondering when you comment on which of those two are the sort of key thing that makes it work.
Yeah.
Like if you constrain what it communicates, say, okay, these are the positions of the neighbors, where they're going.
Yeah.
Or you constrain the other thing. Are they equally important?
Yes. Yeah, it's a great question. We didn't actually do an ablation analysis on that. Well, perhaps my student did whilst we were trying things out, but we didn't report results on them. Certainly something we should do. Yeah. Yeah. Yeah, absolutely agree. For us, it was more like we have this classical problem description, which comes from what the community is trying to solve, and we worked on that, but we could have ablated on, more or less information, just communication or just local obs. Yeah, definitely. Thanks for the suggestion. Let me see. Actually, I will do this slide and then we'll take the break because that's a good moment to take a break. So just so I can wrap up this study. So practicalities tend to be really, really important here. So for this particular paper that I showed you, we generated 30,000 random cases, which consist of random start and end configurations for a system of n agents. We then separate that data set into, I think, roughly 75 training, 15 validation and test. For each case, we generate an optimal solution. Here, an algorithm, CBS, is one of the exact solvers you can use. There are a couple of others. CBS is the one that we use within a given timeout. Parameter updates are done. It's pretty simple, but what's important here, so basically we have our loss function. We update our parameters based on what our current policy is doing. But what's really key is if you think about how do we actually even use this data? Because you can't roll out a policy because each time a robot makes a step and it's the wrong step, the configuration, the board that is actually in has never actually been seen by your expert solver. So you have to actually sample states and actions that have been seen by your expert solvers and solve the problem in that manner. It's a one-step look-ahead problem, and that's how we deal with the data that we have generated, right? So that was actually one of the innovations in thinking about how to solve the full trajectory problem in this imitation learning based approach. We did something called data augmentation, which was crucial to achieving higher success rates. So what we did is every so often, we would look at cases in training that were not solved, lead it to a timeout, and we would look at what configuration of the board the agents were in those scenarios, and we would simply give those situations to the expert solver to have a look at to generate an additional data point. Okay, so we augmented our data during training and in real time, well, during the training process, in order to help with the cases that our current data set was not exploring well enough. Okay, and what I'm going to be talking about after the break is, okay, so what do we do when we actually don't have expert algorithms? And what if imitation learning does not generalize well enough because we just simply don't know what we want to copy in certain situations? And great moment to take a break. That's what we'll be talking about in 10 minutes? 10 minutes. Miguel? Yeah, 10 minutes. All right, see you then.